I left off the last video saying that I was going to go through another example of using the chain rule. In fact, a little bit more complicated of an example. We're going to work on that first, and before we get into our other topic. So this one I actually made up myself because the book doesn't have one of these, but it is something that we should know how this all extends very nicely. So I'm going to write down a variable w that depends on three variables, x, y, and z. It's x times y squared times z. X is going to depend on two variables. X is s squared minus 5t. Y is going to depend on two variables as well, but this time it depends on u and v. But then u and v are actually going to depend on the s and the t that are in x. So u is equal to 7t minus 3s, and v is s divided by t. Finally, z, well, z depends on t. It doesn't depend on s. Z is just going to be t to the fourth. And I want to know what are the derivatives of w with respect to s and t. So there's a lot of stuff going on here. I'm also going to specify here, we're going to find those when s equals 4 and when t equals 2. So those, I'm going to just give it numbers so that we can actually work with things pretty easily. Of course, when we specify what s and t are, we can actually specify what u, v, x, y, z, and technically w are, and that will save us some work overall. But before we do any of that, I'm going to summarize all of this in a tree diagram, and that will make it a little clearer rather than writing out 6 different equations. Though we will have to use the formulas that we have here. So on top, we have w. W depends on x, y, and z. There's a direct dependence on those three variables. X depends on s and t. Y depends on u and v. But then u and v both depend on s and t. So they will get a copy of s and t at the bottom. Finally, z depends on t. There's no reason to write an s down below here. I mean, it technically wouldn't be wrong, but there's no reason to put in extra stuff because that'll actually make the work that we do later a little more complicated. But this gives an easy way of seeing how everything we're going to be doing with w depends on the s and t that we want to work with. So to get from w to s, we have actually 3 routes. We can go from w to x to s. We can go w to y to u to s. Then we can go w to y to v to s. Those are 3 different routes, and each one of those is going to give us another term in our chain rule. For t, we have pretty much the same initial 3. We have wxt, wyut, wyvt, but then we also have wzt. And that's one of the reasons why we don't want to put an s under the z, because it would make it look like there should be another term when we're working with s. And while technically we could do that, it's just that dz ds would be 0 because there's no dependence on s. If we differentiate z with respect to s, it just becomes a 0. We could do that, but it's just unnecessary. And this saves us some thought. But of course, we're going to need to know what all these derivatives are. So we're just going to work out what all those are. First, I am going to go ahead and write down what are the actual values of these variables at s equals 4 and t equals 2, because that will help us out in the long run. So when we plug in 4 and 2 into u, we end up getting what is it? It's a 2. I picked those just to make sure it didn't come out too big here, though we will actually end up with some fairly big numbers overall. V, 4 over 2 is a 2. Don't get a fraction there at least. X is now s squared minus 5t. We can go ahead and plug those in directly. We end up getting 6. For u, we had to plug in the values that we got for u and v. Or, sorry, for y, we had to plug in the values we got for u and v. We end up getting a 10. And finally for z, well, 2 to the 4th power is 16. We go ahead and compute our derivatives. And in fact, I want to do this on the next page. So I start off with, let's just write down the formula for w. W is equal to x y squared z. That means the derivative of w with respect to x is y squared z. And remember, y is equal to 10, z is equal to 16, so we actually get 1600. dw dy, this time the x and the z stick around, the y squared becomes a 2y, so we have 2xyz. Again, using our values of 6, 10, and 16, we end up getting 1920. And then finally, our derivative of w with respect to z, that's just going to be an xy squared. Again, x is equal to 6, y is equal to 10, so we get 600. And I'm going to go ahead and put those into our diagram. Actually, remember to do that this time. So 1600 here, we have 1920 here, and we have 600 here. Those are our derivatives of w with respect to those three variables. Next, we look at x as a function of s and t. Remember, so x is equal to s squared minus 5t. So dx ds is equal to 2s. S is equal to 2. Or no, sorry, s is equal to 4. So we get an 8. dx dt is just equal to negative 5. In fact, we don't even have to worry about what the value of t is. So here, this is 8, and this is negative 5. Now y is equal to u plus u plus v cubed. dy du, well, that's just equal to 1. We don't have to worry about the value of u there. dy dv, this time the u goes away, we get 3v squared. And then v, in this case, is equal to 2, so we end up getting a 12. So we have 1 and 12 for these. We have 1 and 12 here. In fact, I think we never actually used the fact that u equals 2. That never really came up, and it's not going to at this point. All right, moving on. We have that u is a function of t and s. We need the derivatives of u with respect to those. Let's start with s, and then we have t. Now this is a linear function, so it's actually pretty easy. Derivative of with respect to s, that goes away, and we have a negative 3. Derivative with respect to t, the negative 3s goes away, and we're left with a 7. That one's pretty simple. And we can work with v pretty similarly, except this one, because of the fraction, gets a little bit more complicated. So, well, with respect to s, we don't even have to worry about the fraction. it's just s times a constant. The constant is 1 over t. So this is 1 over t, where t is actually equal to 2. The derivative of v with respect to t, this time we have to deal with the fact that the t is on the bottom. The s on the top is just a constant. But we get a negative s over t squared, because the derivative of 1 over t is negative 1 over t squared. Here, s is equal to 4, t is equal to 2. So actually, we have 4 over 4, and we're left with a negative 1. So go ahead and put those values in here. This was negative 3, this was 7, this is a 1/2, and that's a negative 1. And then finally, we need the derivative. Well, let me write out what z is. Z is equal to t to the 4th power. The derivative of z with respect to t. If you want to write that with curly d's, that's fine. I have no problem with you sticking with that. Don't use the regular d's for partial derivatives, just because that people are not going to be as forgiving of that. But we differentiate t to the 4th, we get 4t cubed. Remember here, t is equal to 2. So we get 4 times 8 is a 32. It's the biggest one we got of all the ones except for the ones that came directly from W. So we have 32. All right. So now we can actually write out what are the derivatives of W with respect to S and with respect to T. And we just look at how we get from W to S and T. So going from W down to S, we have this route from W to X to S. As you can see in the diagram, that just starts out with 1600 times 8. Next route, well, here's our next S, so we go 1920 times 1 times negative 3. And then our next route, we still go through the 1920, but this time we go through the 12 and then the 1/2. And that covers all 3 S's that are down at the bottom. I always love it when the program decides to crash. I think that has something to do with the auto-saving, so it always makes me have to rewrite everything that I wrote since the last autosave. So hopefully it's not too jarring seeing it suddenly changed to my new handwriting on my second write through. Oh well, just going forward. So we have this formula that we got by just looking at all the paths from W down to the S's. We go ahead and you can use a calculator for this part, though it is not too hard to do this by hand if you want to. But it turns out to be 18,560 is our derivative of W with respect to S. Of course, a lot of the size of that came from the original derivatives. We do the same thing for W with respect to T. This time we have 4 different T's on the bottom that we need to worry about. So first we do 1600 to then the negative 5. We have the 1920, the 1, and the 7. We have the 1920, the 12, and the negative 1. And this time we do have to worry about the t over here by the z, so we have 600 times 32. And this actually gives us a fairly clean 1,600. And there we go. So ultimately, a lot easier than just having to plug everything into the original function, plugging all 3 of these formulas in for x, y, and z, and then plugging these formulas in for u and v, and having it written out in terms of s and t, and having to do a bunch of product rules and all that kind of stuff. we can just write down the tree of dependencies and work with all the derivatives that are involved there. In fact, since our derivatives were simple enough, we could have just gone ahead and directly written these values into the tree. Maybe the derivatives of w with respect to x, y, and z would have been the most complicated ones to write down, but none of these are really that bad. And we could have just kind of written them in directly. And so that's how I would normally handle that if I were to do this problem just by myself. Okay. So you actually saw an application of the chain rule for a function of two variables specifically back in Calc 1. This is when you learned about implicit differentiation. So a function y of x is defined implicitly if you're given this function by an equation. By an equation that looks like some function capital F of x and y is equal to 0. So if you had something like, I don't know, xy squared plus 5 cosine y is equal to 0. Something like that, where the x and the y are both in this formula here, and you need to somehow extract y as a function of x. Well, the one I've written down here, I don't really know how to solve for y. And you probably have no idea what to do either, because the y that's outside the cosine, the y that's inside the cosine, those are hard to somehow combine on one side without extra stuff. So we say that this function y is defined implicitly. So it's an implicit function. But since we can now write down our formula, our equation for x and y, as a function of two variables equaling 0, we can then differentiate this function using a tree diagram. Here, I'm just going to write the function f on top. F depends on x and it depends on y, but y also depends on x. So if we were to write down the derivative of f, then we'd have the derivative of f with respect to x, just that route going down to x, but then we also have the route from f to y to x. So we get the derivative of f with respect to y times the derivative, well, actually I should probably write this using the regular d, so dy dx. That's the derivative of this function f with respect to x. Just distinguishing that from df dx. This is actually, you could say this is the derivative of the first spot in this function of two variables, whereas what we're really talking about when we're saying the derivative f with respect to x is the derivative of this entire thing, including the y dependence on x. So you have to be a little bit careful when you're mixing the x's in one level of this diagram versus another level. Of course, if the function equals 0, that means its derivative equals 0 as well. And so this is a formula now for the derivative of y with respect to x, because that's usually what we're trying to find. We're trying to find the derivative of this function here. So we'll go ahead and solve this for dy dx, and we get this formula. So all we really had to do was move the df dx to the other side. That means we get a negative df dx, and then we divide by the df dy. And so that's exactly what we have here. Or if you don't like having this written out as in the curly d notation, you can go ahead and replace df dx with f sub x. So we have negative f sub x over f sub y. And it turns out that the only real obstruction here, and I guess technically there's a couple of obstructions here. The first thing, of course, is the derivative with respect to y can't be 0. If that's 0, we can't divide by it. And so we wouldn't be able to solve for dy dx. The other thing here is to make sure all this works out very nicely, we actually require the partial derivatives of the function f to be continuous. And we get what we frequently call the implicit function theorem. And the condition about having continuous partial derivatives really just says that as long as we have that, then the implicit function y is actually a differentiable function, and its derivative can be given by this formula. You don't have to worry about the condition about continuous partial derivatives. The main thing to worry about is whether or not whether or not f sub y is 0. If that's 0, then obviously the formula breaks, and it should be fairly obvious in that case that things aren't going to work out nicely. Now, it turns out that we can also do this for a function of two variables. If we have a function z of x and y that's defined implicitly by some function f of three variables that equals 0. So maybe here we have x, y, z plus e to the z minus, or we can even say equaling 5. Let's just do a cosine again. There we go. So once again, we have a formula for x, y, and z, relating them to each other. We can't really solve for z very easily, but that doesn't mean that z can't be described as a function of x and y. It's just defined implicitly. The fact that we have 5 cosine over on this side, that it's not equaling 0, doesn't really matter. We can easily just move terms that are on this side over to the other side. We can just rewrite this as xyz plus e to the z minus 5 cosine of x equals 0. So normally you'll see equations where they're not necessarily equaling 0, but we have to first do one step of moving everything to one side. And we do that step just to make sure that we know what the function f actually is. So the function f here is not x, y, z plus e to the z. It also includes the term negative 5 cosine of x. But the point here is that f depends on the other variables x, y, and z. And then z depends on the variables x and y. And in order to differentiate or to find the derivatives of z with respect to x and z with respect to y, we look at the derivatives of this f with respect to x and y. So the partial of f with respect to x. Well, the derivative of f with respect to x, first we have the route from f directly to x, but we also have the route from f to z to x. So we start off with this term that's directly there. We can ignore the y in the middle, actually. Then we have the one where we had the partial of f with respect to z, followed by the partial of z with respect to x. This actually is a partial derivative this time. And of course that equals 0 because the function equals 0. We can do the exact same thing with y. We can either go directly from f to y, or first go to z, and then from z to y. And that's still equal to 0. And then, of course, we go ahead and solve. So we get that the partial derivatives of z with respect to x and with respect to y are just a quotient, or, well, negative of a quotient of derivatives of f with respect to x and z, and with respect to y and then z. Of course, again, we do have the condition that this derivative of f with respect to z not be 0. If that was 0, then obviously the formula breaks. And technically, to make sure everything works out nicely here for this version of the implicit function theorem, and the implicit function theorem is quite a general result. We're just looking at two special cases in 2 dimensions and 3 dimensions right now. But for this version of the implicit function theorem, again, we technically require that we have continuous partial derivatives of f, though we usually won't really worry about specifying that. Usually that'll be just fine for any examples that we're going to go through. The main thing is that df dz needs to not equal 0. So let's put these to work. We have a function here, a function y of x, defined by this implicit equation. Of course, it doesn't equal 0 right now, so actually our first step would be to put everything on one side, so that we have an equation in terms of x and y equals 0. This is our function f of xy. And we want to use this function of two variables, to find the derivative of y with respect to x. Of course, recall what our formula is. The derivative of y with respect to x is equal to negative the derivative f with respect to x over the derivative of y. Derivative of f with respect to y. So I'm just going to start off by finding these derivatives. Derivative of this with respect to x, well, the -1 negative sign go away. We don't need those for this part. Derivative of cosine is a negative sign. We keep that same inside in here, but then we have to multiply by the derivative of the inside. Derivative of xy with respect to x is just y, because the y here is a constant that's being multiplied to x. So we have negative y sine of xy. F sub y, we do the same thing. The derivative of cosine is negative sine. We still have the xy inside. The derivative of xy now, because we're differentiating with respect to y, is going to be x, because the x is just playing the role of a constant. Again, the -1 goes away, but now the negative sign of y actually gives us something, so derivative of sine is a cosine, and it stays negative. We're going to go ahead and plug those in here. We saw the negative out in front. We have a negative y sine of xy on top. We have a negative x sine of xy minus cosine of y on the bottom. And I'm going to do one simplification step. I'm going to use the negative out here to just get rid of the negatives on the bottom. Fortunately, we can't cancel out all the negatives. So the top will stay in negative y sine of xy. Bottom will be an x sine of xy plus cosine of y. And there's really no simplification that can be done there. That's just our result. This is going to be true anytime this denominator, this x sine of xy plus cosine of y, is not 0. Of course, figuring out exactly when that's going to be true is maybe a little non-trivial. I guess, let's say, if x equals 0 and y equals pi over 2, then that'll make everything 0 on the bottom. So this formula wouldn't work at the point 0 pi over 2. Let's just say that. Of course, we could have gone ahead and differentiated the formula directly, like we did in Calc 1. So just differentiate cosine of xy. Just in that case, we have to remember that we're using the chain rule, and keep in mind that when we differentiate x times y, we're differentiating a product, and all that kind of stuff. When you do it like we did back in Calc 1, you have to make sure that you remember at every step that you're working with y as a function of x, and it can get a little complicated because of that. You have to remember chain rules at places where it doesn't necessarily look like you're using a chain rule. I find that this technique might be a little bit more easy to remember if you remember the formula, though of course it does require you to remember the formula. So which technique you favor is up to you. It's just another way of approaching it. Of course, when we move up to working with a function z of x and y, we're going to have to use our new formula. So let's go ahead and take a look at one example like that. So here, z is a function of x and y, but it's defined implicitly. Of course, our first step, like on the previous problem, is to move everything to one side. So we have yz plus x ln of y minus z squared is equal to 0. And this is our function f of xyz. I'm not going to write the xyz part in there, but this is f in terms of x, y, and z. We're going to need to know all the partial derivatives of f. We'll go ahead and find those before I write down the formulas. Derivative of f with respect to x, well, the yz and the negative z squared don't really matter. They go away. But we do have the x ln of y, where the ln of y is a constant. So actually, this is just going to be ln of y. F sub y, this time it's a little bit more interesting. The yz becomes a z. The ln of y becomes a 1 over y, but we still have the x there, so we end up with an x over y. And then we have the negative z squared that goes away. Finally, f sub z, this time the yz becomes just a y. There's no z's in the x ln of y, and then the negative z squared becomes a negative 2z. If we go ahead and write down our derivatives of z with respect to x and y, derivative of z with respect to x is a negative of the f sub x over f sub z. So f sub x is ln of y. F sub z is y minus 2z. And I forgot that negative. I'm going to go ahead and use that negative and just switch the order of this difference. So we have ln of y over 2z minus y. Derivative of z with respect to y this time. Very similar thing, except now instead of x we use y. Derivative of f with respect to y is z plus x over y. We still have y minus 2z on the bottom, and we still have that negative out in front. I'm going to go ahead and simplify this a little bit more than last time. So again, I'm going to use the negative to flip the order here. But because I don't like having fractions inside of fractions, I'm also going to multiply the top and bottom by y to cancel out the y that's down there. So this z is going to become a yz. The x over y is going to become an x. I'm putting these in the other order, so the 2z that's in front is going to be multiplied by y, so I have a 2yz. And then the negative y at the back is going to become a negative y squared. And there we go. Those are our derivatives of z with respect to x and y, this implicitly defined function. Now, of course, it breaks is if f sub z is ever equal to 0. So whenever y is equal to 2z, this doesn't work. But why does it break there? Let's actually look at the surface that's defined by this. Note that GeoGebra doesn't like to graph implicit surfaces, so if I just plugged in the formula yz plus x ln of y is equal to z squared, GeoGebra probably won't have any idea what to do with that. So I'm actually going to take a technique from chapter 16 to show this to you. This is actually somewhat similar to how we define curves using parameters. We can actually parameterize surfaces, and so that's what I'm going to be doing here. But in order to do that, we end up having to use 2 parameters instead of just 1. I'm not going to bother to explain that right now, but we will be seeing it in the future. So this is the surface that's given by that equation. At least up to a point. It actually is a little bit nicer than what GeoGebra can display here. There's actually not a gap here. It actually does close up there, and in fact, it closes up over here too. It's kind of like a it kind of has a little narrow neck here, but it has a part over here and a part over here. But it's kind of a weird looking surface. If you were to plot our condition that was our problem condition, remember that was when y is equal to 2z. And that's actually going to be a plane. All the points in all of three-dimensional space that satisfy that as a plane. Of course, we're only really concerned with the points that are actually on the surface. And that's given by a curve. And let me just go ahead and plot that curve. GeoGebra doesn't really like intersecting the surface with the plane very well, so I'm going to have to write out my curve explicitly. And I think I made a... just a second. Oh, I see what I did. I left out my z component. So it wasn't plotting it in three-dimensional space. It was actually plotting in the xy plane. Let's make this a little bit darker so you can see it better. There you go. In fact, we don't really even need the plane in there. So we have this curve that's on the surface, and you can kind of see where GeoGebra isn't really displaying all the surface because it looks like the curve goes off the surface. But in fact, that curve does actually stay on the surface the entire time. And you can wonder what exactly is special about those points that makes our derivative not work there. Well, if you really pay attention to it, at every single one of the points on here, we actually should have a vertical tangent plane. And it might look like maybe points over here should have them, but really they don't. These are actually slanted a little bit. It's not directly up and down over there. But at the points on this curve, we actually would have a vertical tangent plane. And, well, that's going to break things. That doesn't mean we actually can't work with vertical tangent planes, but we're going to have to wait until we can actually talk about these parameterized surfaces before we do that. But with our implicit function theorem, really our condition about having the stuff on the denominator not be 0 is really just saying we don't want to have to deal with any vertical tangent lines or vertical tangent planes. Those are really our obstacle. So it's always really nice to know when some condition that seems pretty obvious from our formula really does correlate to some geometrical problem, some geometrical obstruction or obstacle to actually working with stuff. So it doesn't, even if it just looks like, well, we can't divide by 0, and that's all that's really we're saying. No, there's really actually an issue with the pictures where we can't do anything better. At least not with this particular technique. Alright, but that's really all I have to say for that. I'll go ahead and leave this here. Hopefully you got a good idea of how all this stuff works and how to actually work with the chain rule for really any sort of function of multiple variables with nested multiple variable stuff inside of them. You can get really crazy with it, but there's not really any point for us to really say anything more. So I'm gonna go leave that here. Yeah. So I'll see you guys next week.